Good afternoon. My name is Łukasz Augustyniak and I will present today, together with Piotr Szymański, our latest paper entitled Punctuation Prediction in Spontaneous Conversation. We are especially interested of possibility to mitigate ASR errors using retrofitting of word embedding. I will present the description of problem, so why punctuation matters, especially in transcription of call center data. Then we will talk a little bit about ASR errors. And in the second part, Piotr Szymański will present our approach with retrofitting of word embedding to improve punctuation prediction. He also described the results and our conclusions. So, punctuation truly matters, especially if we see the example like here. So first is without any punctuation, let's eat grandma. So somebody just want to eat grandma. And second example shows that with punctuation, so with comma after the it word, it changes the understanding of this sentence or part of this sentence dramatically. And similarly, in second example, we have I love cooking my family and pets. So somebody is really a fan of eating family or pets. However, with properly punctuated example, we see that somebody just love cooking, also love family and pets. Punctuation also influences the performance of natural language processing models, such as named entity recognition or keyword extraction. And interestingly, we evaluated the same text example without punctuation and with proper punctuation using spacey named entity recognizer. And we see that, for example, in the text without punctuation, the tool didn't find Lucene technologies like the organization, and we have that in the text with proper punctuation. And interestingly, Avaya Interaction Center without punctuation has been extracted as facility, and with punctuation it is like the organization. Yeah, so punctuation influences tasks in natural language processing area. And of course, text without punctuation is much harder to read. Going further, especially in spontaneous human-to-human conversation, the word error rate will be like between 15 up to 20%. And in call center data, if we have a lot of noises, people are calling to call center from different places with different environments and etc., it could be even higher. So what kind of mistranscriptions we can get from the ASR systems? So the sentence "thank you for calling XYZ company" could potentially be transcribed as "think for calling, thank for recalling, think for holding, either thank you for going." So we're changing almost every word in this part of the sentence. And even in the worst case scenario, we can get something like "and give her going," which sounds quite similarly. However, the words behind that are completely different than it was in the the proper sentence. We can spot here a couple of homophones. A homophone is a word that is pronounced the same as another word but differs in meaning. For example, think and thank. Nowadays, word embeddings are standard vectorization technique in most of natural language processing tasks. However, they do not contain any information about homophones' proximity. We wanted to improve word embedding layer of our punctuation prediction model to represent specifically homophones closer to each other in the embedding space. We used a retrofitting method called mittens and transcriptions of calls to improve glove embeddings. More about retrofitting and results of our improved model will tell you Peter.
Hello everyone, my name is Piotr Szymański and I will follow up on the results that we've managed to obtain in this contribution. The problems Łukasz was talking about arise in different levels of modeling, and downstream tasks, but were very visible in punctuation and in detecting how similar substrings in our data are. If you look at 7 to 10 word sequences in spontaneous conversations, you will see that they differ strongly to what is present in books or other textual data present on the internet, which are used to train language models or vector representations. We wanted to tackle this problem because originally the language models did not work well with domain data in domains that our clients' businesses operate, and also were not really resilient toward speech recognition errors. We wanted to improve the similarity of words, of the representations, cosine similarity, but also we wanted to improve through this other tasks that we deploy models for. It is important to note that our motivation was technically limited. We needed a very small memory footprint and CPU footprint model with very low latency, so we did not want to use sophisticated techniques such as BERT transformers or even attention models. We even looked at LSTMs as models that might end up being too costly. So the natural thing to do was to work on representation learning and updating the language model for our tasks. And what we found was a method called Mittens for retrofitting glove vectors, published by Nicholas Dingwall and Christopher Potts from Stanford. And they used it for improving language models in their medical startup or the medical company they worked for, because they had a lot of domain data that were not present in the original glove embedding, so was not present in such contexts. And we could have trained golden transcripts, this on golden transcripts, but we didn't because we saw the opportunity, knowing how ASR errors are structured, to use contexts as a proxy for improving, for tackling the resiliency to speech recognition errors, transcription errors, because often words that sound similarly or phrases that sound similarly, they happen to be present in the same context, and we could mitigate this kind of error. So, and this is depicted on the drawing that you see on the right, the figure on the right, the retrofitting process, which basically consists of taking the original glove vector and mixing it with a new vector which is trained on your new data, and this mixture is controlled by a mixture level parameter, and then such a criterion is optimized, so you get new vectors from the new ones learned mixed with the old ones. And as such, we've managed to group together clusters of words that sound similarly and appear in similar contexts, such as thank or think, as you saw in previous examples. They are usually not similar in language models trained on Wikipedia texts, but they are in spontaneous conversations. And we've managed to extend the model architecture with additional proxies for audio characteristics. So we wanted to be able to take into account speech dynamics, such as how long it took to speak, to utter a certain word, or what was the speed with which it was uttered, to proxy for intonation changes, because as many other people showed in their work, such additional features allow better detection of whether to put a question mark at the end or a full stop at the end of a sequence of words. And we end up classifying each word separately, whether with a punctuation mark or not. We also added information about the side of the conversation that uttered the word, so whether it was an agent or a customer. We wanted to show this on a publicly available dataset, or at least one that's widely established, and so we use the Fisher dataset. This is a strongly imbalanced problem, so 80% of words do not have any punctuation marks, and we have commas which are more prevalent but of lesser importance in real-world applications, and we have full stops and question marks, and there are 8 times more full stops than questions in the dataset. And with such a dataset, we wanted to see how our method compares to a standard CNN baseline and a BA-LSTM baseline that we didn't want to use because it had too much of the memory and CPU footprint. And also, and we wanted to compare those baselines with 3 variants of our models. The first parameter we wanted to control is whether we want to add a full vocabulary, so 100,000 words, or we just want a 50,000 word vocabulary, which again takes less memory. And the other parameter was whether we use the mittens retrofitting or not. And just by using the retrofitting approach, we've managed to improve precision and recall on most classes. We even managed to perform better than BLSTMs in terms of F1 for the 2 most important punctuations, so full stop and question mark. And those are very important because they have the biggest impact on readability. So this is what the user will see, and this will improve the comfort in reading a transcript. But also they are responsible for allowing us to segment otherwise unstructured text into something that can be further used in with downstream NLP models. The improvement in accuracy for full stops has been 9% and 9 percentage points, and 6 percentage points for question marks, and those are really interesting improvements. They allowed us to have a visible effect in readability, and in the future we would like to investigate the statistical effect on how models, how this impacted model performance. We also got much better from our point of view, from our exploratory needs, much better results in similarity analysis. The retrofitted homophones and oronyms are close to each other with cosine similarity, so we can have sequences of words that were mistranscribed but still being able to explore them in an efficient way, especially in contexts that are actionable, such as buy or intents, where someone wants to cancel and definitely not cancel, and also with standard phrases that are sentiment important, like thank you and think you, or legal threats like go to the court and go to the cart, and all of this similarity has improved here. So as a result, we used a domain alignment method for word embeddings to mitigate ASR errors and to get strong improvement on 2 most important punctuation marks in the punctuation prediction. But this is just a use case. This method actually allows us to get improvements in nearly every task that we've been tackling in natural language processing, both with basic neural architectures and with more advanced architectures. And in the future, we plan to evaluate the impact of this on downstream NLP tasks. But we already have a paper out for that describes ASR errors impact on the level of ASR errors, which we highly recommend to read. It's been accepted to EMNLP this year. So take a look at that, and also thank you for listening, and if you have any questions, we're very open. Thank you.